All right, welcome back, everyone. Happy Halloween. If you're into that, keep it safe. um, Maybe you already celebrated over the weekend. If you do those, we'll see. Um, I'm still working on well, I will start working on. I had 2 exams from my other class that were earlier in the week. I'm halfway through the MAT171. As soon as I get through those, I will get working on scoring your exams. It might not happen until this weekend. Got home last night, worked on them a little bit till I got cross-eyed and I couldn't see straight anymore, so I said I got to get to sleep. This morning, other things. So anyway, we'll get working on them. But what we will do is we'll move forward. We're getting into 4.5, so there is not another exam until the final. And the final is comprehensive, so regardless of how you did with 1 or 2, you have basically a chance to improve, certainly, or do the same or better, which is what we'll look for. It was brought up to my attention there are review assignments for the exams. I had forgotten about them, and I don't intend them to be part of the homework grade. I think they probably are at this point. What I will do is I'll separate them out and I will make those extra credit. I will see, I don't know how much, but I'll see whatever the amount of extra credit I allowed to give out. Usually it's 1 or 2%, so it's not extraordinary, but it's something. I will make those reviews worth that full amount. And again, I'll do the same thing. You'll get full credit for the reviews if you get it to, is it what, 80% or 70%? 70%. Okay. Each class negotiates a little something different with me, so you guys got me down to 70%. The calc class I only left at 80. Yes. Yes. Also, yeah. So whatever's for the homework, we'll keep it for the exams and exam reviews. And again, they're good. Again, if you don't do them, they're not going to hurt you, but they're good reviews to hopefully help with the test. They're not exactly like the test, but they've got the concepts in there. They'll help with the final, getting you the concepts, all that kind of stuff. So the more you can learn, the better off you're going to be, especially as you go into calculus. Because usually the problems that students have with calculus, the problems I had with calculus, were not so much the calculus, it was all the algebra and the trig that you have to do to the calculus stuff. The calculus steps, generally, some of it you just memorize certain things and boom, the calculus is done. But then you've got to do some algebra or trig stuff to it. That's the harder stuff. And so that's what we're getting you the basis for. You'll get more practice for it in calculus. So I always thought I want to master something before I move on, but it never happens that way. If you don't move on, you won't ever master it. You master it in the next step. So keep working and keep moving forward. This morning I recognized that I hadn't even opened up the modules, so now they're open. So this is the first thing we're going to take a look at. We're going to look at graphs of sine and cosine methodically. That's all we're going to study, but then we look at the other types of trig functions. But we're going to get into graphs to start with. There's a few nice animations and stuff here that we will take a look at. But what I'll do is I'll go through the oops, no, not that yet. I will go through the sort of the presentation part. We'll introduce everything, and then we'll play. I'll show you that we've got these animations that I highly encourage you to click on and play with, because they'll help you understand as you go through this stuff. So, graphs of trig functions. We're going to create signs of sine and cosine. But what I want to do is, we've been talking about the unit circle, and we did that on a coordinate system, right? And we've been talking about the functions as they relate to x and y values on a rectangular coordinate system. Well, when we go to talk about the graph, we are looking at sort of a different type of graph. So I want to set that up with decimals, and then we'll see how that all relates. So when we go to graph sine, we're going to, and I'm going to do this sort of point by point. I'm going to set up a table. X will be where where we define x to be the angle that we're making with the x-axis. Y will be the sine value, so I'm going to put in here sine of x1. So as I put in values for x1, like 0, so the angle could be 0, sine of 0 is 0, and so that got plotted here, 0, 0. What's the next special angle we have going up in radians? Pi over 6. So I'm going to type in pi using just pi, turns it to pi over 6, and that's 0.5 or 1/2, and notice at pi over 6 we got there. What I'm going to do, I almost forgot about this, but I want to show you something that's really cool with Desmos that I found out with a student. So what I want to do is that x-axis, wouldn't it be nice if it gave me numbers instead of 1, 2, 3, 4, if it gave me numbers in terms of pi? It can do that. So what I do is I'm going to step by, let's do by pi over 4. You could do pi over 3, pi over 6, whichever way you want to step. And then let's go from maybe negative 2 pi to positive 2 pi. And I'll just leave the y-axis as it is. But notice now my x values down here are all in terms of pi. Pi over 4, pi over 2, 3 pi over 4. And again, you can change that as you want your steps to go. This is going to be helpful as you go through going forward, because we're going to actually be able to solve things by graphing. And we can use Desmos. Now, Desmos, unfortunately, you can't use on the test, but it will help you get the concepts down, and then you can translate how that works with the TI-84. And now that I've done that, notice when I click here, my x-coordinate is pi over 6, 1/2. Okay. What's another special function or another special angle after pi over 6? Pi over 4, pi over 3. So we'll count here. Pi over 4. That got plotted. Pi over 4, we're at 0.707, which is square root of 2 over 2, right? And then we could do pi over 3, 2 pi over 6 if you want. And we got that, which is square root of 3 over 2. And again, it's plotting it for us. And then pi over 2, which is 90 degrees. And so we see this thing happening. I guess what we could do is also make it look a little prettier. We'll have our y-axis maybe go from -2 to +2, so we can get a little bit better. And then we come around the other side. Let's see, that would be 2 pi over 3. Oops, where is it? And we get that one. And then 3 pi over 4. We get that point. And then 5 pi over 6. We're there. And then pi. So we've gotten sort of one thing, and then we'll come back. Can you recognize that now sine is going to be, we went halfway around the circle, we come the other half, the sines are all going to be negative, so we'll get a similar thing going here. But what I want you to see is the graph we're getting is switching what we've been doing. X is now an angle, the y is the sine, is the function value. And we'll do that with both sines and cosine. So back to here, this is what we've done, is we've basically taken the unit circle, we've taken all the special angles, we put the y values are the function values, the sine values, and notice, yeah, after pi, all the sine values are negative, so you get that bottom half. So we would, if we would have continued, we get the dots kind of going like this as we go through. And again, it's tedious and methodical, but it helps you focus and see that this is what this graph is. And what I see is the biggest misunderstanding is students will connect it to that unit circle, which we're using those values, but we're graphing differently. X and Y are different things here. In the unit circle, X is a location of a point on the unit circle, right? Y is a coordinate on the, so X and Y are kind of the same thing. Here it's different. X is a angle value, so it's more abstract. And then if we basically put all the other angles in, this is what we get, this smooth curve. So this is our sine function, and we're going to kind of compare, we're going to manipulate it as well, so everything is going to be either sine or cosine. Is that sort of clear? Getting there? Okay, and again, as we work through it, but that's the first thing you've got to understand. So when we're talking about the graphs, the x is an angle, the y is the function value, sine of that angle. And we're plotting it. It's something different than the unit circle that we've been using, and we've been using that to understand. And I got through trig without understanding that. That's why I messed up so bad. It was harder than it needed to be until I picked up that. So some of the things we see, get this out of the way. So the sine function, it's got a domain of negative infinity to infinity, right? Because we can, remember, it's an angle. We can keep going around that circle, so we can make angles in both directions from negative infinity to infinity. But as you saw with that graph, the highest sine ever goes is positive 1. The lowest it ever goes is negative 1. Okay, and we see that right here on our functions. You know, that's our highest value. There's our lowest value, and we get sort of these wave functions. And it's actually, you can use sine and cosine to model the ocean waves. Anything with a wave type function. We're here. Sound is a wave. Sound waves, we use sine and cosine to model sound. Lots of different things. Electrical impulses, they're actually wave functions. Okay. Creating the cosine function, we're going to see is very similar. We would do the same thing, but cosine of 0 is what? 1. And so it's going to look a little different. Oh, I forgot I had an animation here. So it's coming off of the unit circle, right? The values, as you kind of see it traced out here. But so it would start at 1, it goes down at pi over 2 it's 0, at pi it's negative 1, and so it goes on and on like that. So there's an animation. There's another animation we'll show you just to kind of get you this connection. So it's like, remember, the unit circle still exists, but it's over here in a different graph. This is a new graphing system where x is an angle now, not a coordinate on the unit circle. So graph of cosine, here's all the cosine function values. And again, these are in your notes. And, you know, so it follows what cosine is. If you do the points, cosine starts at 1. Remember, sine started at 0. We're going to compare the difference. But again, you get this wave function. And then if you throw in all the angles, you get a smooth curve for the cosine function. Okay, so basically same thing, but notice sine and cosine are a little different. How they're different, one thing that's not different, they both have the same domain, and they also actually have the same range, where the highest of the cosine is positive 1, the lowest is negative 1. They occur at different places, but they're pretty much the same. Okay, so that's what we're going to look at. I was going to do this one at a time, but sine and cosine are actually very similar. They're just really shifted functions. So if you were to shift the sine function by pi over 2, so notice that pi over 2, if we were to move it to the left pi over 2, the functions would be the same. So that's why we could use, a lot of times we're going to give these real world type problems, we can use either sine or cosine, just depends upon where we're starting. Okay, because they have exactly the same shape, it's just that where they start is different. Okay, but if you moved them, they would actually line up one on top of the other. And if you graph cosine of x and sine of x plus pi over 2 in decimals or anything, you'll see that they're right on top of each other at this. Okay. So we're going to look at a few examples, and again, these come from the notes. But so the cosine function, so this is 4 times the cosine function. So let me just draw a little sketch here. So remembering the cosine function looked something like this. It started at 1, kind of came down, went up, went down there, and there, something like this, right? Where this is 1. What is this 4 times the cosine going to do? Moves it up, but it also does what? It stretch, yeah, so it's a vertical stretch. It will move, so it multiplies. The best way to think of it is going to multiply every y value by 4. Everything will become 4 times bigger. Of course, 0 still stays 0, right? So what's going to happen is this, instead of being at 1, is going to be up here at 4. And this, instead of being at -1, is going to be down at -4. And 0 will stay at 0. And fortunately, I've got a graph of it. It'll stretch. Okay, this is something that we're going to call so it's a stretched function. This we call amplitude. And we would say this function has an amplitude of 4. So from the top to the bottom. And it basically, if you take the top to the bottom and divide by 2, right? +4 to -4 is a distance of 8 divided by 2. That's the wave height. And so with waves, you have a height of 4 feet, but you also have it going down 4 feet. So the difference between the top of the wave to the bottom of the wave is actually twice the amplitude. So you got to be careful. When they say it's a 100-foot wave, does that mean that the amplitude's 100 feet? That means it could actually be 200 feet from bottom to top if you're a surfer. That's any surfers in here? All right. Would you take on a 200-foot wave? No. I have problems with 10-foot waves. I think maybe a 1-foot wave would be okay. But did some body surfing in Oregon, but that's, when we're kids, you do crazy things. And good. Okay, so what it looks like is this. Again, a little bit better drawing. It's going to stretch it by 4, so amplitude. So we're going to look at that's one way. So basically, we can model every type of wave activity with either sine or cosine, but we might need to adjust it some way. One way is adjusting the amplitude. Okay. And we'll talk about all these. But yeah, it's just the cosine function, vertical stretch. Oops, I wrote over the top. Let me back up. Here's an example, -1/2 sine. So what would that do with the sine function? Good, that negative flips it. So standard sine, let's just kind of draw what that would look like. Standard sine, remember, goes up and comes down and looks something like that, starts at 0, 0. So it should flip it and then compress it by a half. And we look at the graph. Yes, instead of going up, it goes down and then up. So that was the flip. And then the amplitude is a half. So we see it going from -1/2 to +1/2. It's been compressed. Okay. And when we talk about the amplitude, we talk about the absolute value of that number. So it's 1/2. The amplitude is a half, which means it's a height of 1/2 or a drop to 1/2. But that negative is important because that does give us a reflection, a flip. Yes, sir.
Is there anything specific you can find from knowing the distance between the tops of the peaks of the waves?
The distance between them divided by 2 will always be the amplitude. The importance of that is specifically is the height from the low to the high, and it depends on what we're modeling. Again, in the ocean, it's very clear that we're that's the distance, and so when you're designing boats and stuff, you've got to say, okay, if you know the amplitude, it's a boat's got to be able to handle actually twice that, because the amplitude is only half of the height, the wave, the other half is the bottom half. And we can use it, it depends on what applications it's being applied to, what kind of wave. But yeah, if you know the amplitude, you know that actually you have to account for twice that amplitude as far as change. I think is the main thing. So this one we still have an amplitude here, right? That's going to stretch it vertically. Yes.
So to find the height, you just add the amplitude twice, or do you multiply it by?
Both will work. Good question. So 4, you could add 4 to 4, and that's kind of a nice way to multiply. You could either take 4 times 2 and you get 8, or 4 plus 4 is 8. So adding them together twice will be the same thing as multiplying by 2. Yes, and that gives you the distance from the top to the bottom. Sometimes they give us that distance, let's say like the wave is the total distance. So then we would say, okay, to model this, we need an amplitude of half. The amplitude would be half of the distance from the top to the bottom. So we kind of go both ways. Depends upon what information they give us. So what we do know with this one, we have an amplitude of 3. So that is a vertical stretch of 3. What's this 2 on the inside going to do? Because that's the new thing. If we added or subtracted, that would move the starting position. You're on the right track, though. It does move. It has an effect horizontally. Is it going to compress or expand? Do we multiply by 2? Think about transformations when we're inside the function. Remember, we always do the opposite. It's going to be a compression, a half compression inside. So the other thing we didn't talk about too much, but we should, is what we call period in a graph. Period is how long it takes the graph to repeat. We're doing cosine, so I better draw a cosine here. So cosine starts high, goes low, comes up, and is back here at 2 pi. So we would say pi has a period of 2 pi, because after 2 pi it repeats itself. Okay. What this is going to do is it's going to compress it so it will repeat itself in less than 2 pi. And notice we go from the high point back to the high point here. We do it in just pi. So what has happened is the period which was 2 pi, we divided that by 2. So this number here is what goes in the denominator, and our new period is just going to be pi. So we're going to see this concept, and we've got a slide that puts it all together, helps us to figure out the period of a function. And that tells us how rapidly the function's going, right? So a smaller period means more rapid change. A larger period means slower waves. Okay? So, and again, we'll put this all together. But that's all the different types of transformations. And we've got a nice little applet that you'll be able to play with, and you'll be able to change each of these, and you can watch the graph grow. And so some of this we're just kind of seeing what you remember from transformations, and we're getting them applied here. So multiplying on the outside, we'll do a vertical stretch or compression. Multiplying inside does a horizontal stretch or compression, but it's opposite, right? If we're multiplying, it compresses. When we divide, it will stretch it. And then the last, well, I don't know if this is not quite the last one, but the other thing is if we add or subtract inside, this will be a vertical translation. It will actually move the graph one way or the other. We sort of did that with sine, right? If we put plus pi over 2, that moved it back to the left and lined it up with cosine. So any addition or subtraction inside here is going to, bless you, move it in a direction. And so notice this is negative. So it took the standard sine function and it moved it pi over 4 to give us this new one here. So the black one is x minus pi over 4. This is something we call phase shift. So it's shifting the phase of the waves. Okay, so that'll be a vertical shift that way. What's left? Stretch, compress, shift it horizontally, shift it vertically. How would we shift it vertically? Adding or subtracting on the outside. Very good. So then we could put a number out here, and we would move it up 2. Okay, so that's the effect it would have. Or if you subtract a number, it moves it down 2. I don't think we have an example for that, but here it is. So here's our basic, the main things we look at. But yeah, if we any of these, if we add or subtract, we could also move it up or down. So the key features we have is the amplitude is the number a in front of the sine or the cosine. Again, they work pretty much the same. When we get into modeling applications, we want to think that cosine starts at 1 and goes down, sine starts at 0 and goes up. So it depends upon what, sometimes we'll use sine because that's what the details tell us. It's sort of starting at 0 and going up. Sometimes we'll use cosine because that's the better fit. We could use both, but we'll see both things happen the same way. So whatever this number a is in front, that's going to tell us the amplitude, which remember, amplitude is sort of half of the whole total wave. If we double it, we get from the top to the bottom. Okay, and then it talks about if a is negative, if we have a negative on there, it will also reflect it over the x-axis. The value of b is not the period itself, but if you take 2 pi divided by b, like we did on that one, we get the new period. Okay, and again, that's a compression or a stretch horizontally. So whatever b is, we divide by 2 pi, and we get the period. Sometimes they give us the period, and we need to come up with the function. We'll be doing ones like that. So you'll want to kind of use this as an equation. If we know what the period is, we can figure out what the number b is. And then we could come up with that function. Sometime from the graph, they want us to get it. So, okay, we could maybe measure that amplitude, and then we could come up with the function. The hardest one to see is the phase shift. The way they have this, it's going to be, it's not a direct thing, because if there's a number here, it's going to be c divided by b. On that example that they gave us, I think they had sine x minus pi over 4, something like that. So b is actually 1 here. There was no, the period wasn't changed, but it was a phase shift of pi over 4 divided by 1, which is just pi over 4. And again, we look at the sign. So if it's negative, it means it's actually moving it in the positive direction, so it moves it to the right. If it was positive, it would move it in the negative direction, which would be to the left. So a negative phase shift means a move to the left. Positive means a shift to the right. So these, again, are concepts we picked up earlier, but now we're putting them into trig and seeing how we are able actually to create a function that will model any type of wave, any shape of waves. And okay. So find the amplitude, period, phase shift for the function 2 cosine this. Okay. So what's the amplitude? How do you know? Because it's right there, right? That number in front will always be it is. Does it have a reflection? No, there's no negative, so the amplitude is 2. And again, this works both ways. Sometimes they will tell us the amplitude's 2, give me the function. So 2 times cosine, and so we have to make it up. But if they give us a function, we say, okay, it's going to have an amplitude of 2. So part of this is you're going to say, okay, when I start thinking of the graph, I can visualize it. It's going to go from +2 to -2. Then we look inside. How about the period? Good. So period, remember it's 2 pi over b equals the period. B is pi, so it's 2 pi over pi. Pi cancels with pi. We end up with a period of 2. And so it's 2 radians. So this is 1 and this is 2. It's done a full period in 2. There's no pi there. It's just 2. How about the phase shift? Now remember, this is C and this is B, and we have to take C divided by B. So that's going to be pi over 2 divided by pi, which is equal to pi over 2 divided by pi over 1. You flip and multiply, so pi over 2 times 1 over pi. Pi's cancel. It should be a phase shift of 1/2. Very good. So part of this, yes?
How did you find that A equals 1?
Up here?
No, like the question is 2 cosine bracket pi x. Was it multiply or split? The last one. The question is like y equals to 2 cosine.
So which one are you talking?
This one. Y equals to cosine bracket pi x. Oh yeah.
Oh, here. Okay. So, okay, so what this is saying, I guess I should do. So the A is 2. That's the number in front. B is going to be pi. And C is going to be pi over 2. And then I can come up here and I sort of use this that the period is equal to 2 pi over b. The phase shift is equal to c divided by b. So for phase shift, I did pi over 2 divided by pi.
For the phase shift, do we have to put -1/2 between the finger and the left, or does that, or does it just want to know the increments of how much it's shifting?
It wants to know the increments, and then, but then we go back and look at it. So thank you. Direction's important, so that's 1/2 to the left. So we do have to somehow mention that. Yeah. You got, okay. So again, a lot of the homework is we're given a graph. Maybe we have to find the amplitude and the phase shift, but those on the graphs will be able to see them. Or we're given something like this, and we're asked, so, and then maybe we're asked to graph it. Again, we always use the graphing calculator, but since it's cosine, it's going, and it's got a period of 2. It's got to go, I think it's got to go like this, and this, and this. So that's one period within 2. And actually, I didn't get the phase shift in. It should be shifted 1/2 to the left. So this should actually be over here at 1/2. So it would come down and be moved over. And sometimes they're hard to draw, but you could kind of visualize it. And we're going to, now that I've drawn all over it, this is what it looked like. So it has been shifted to the 1/2, and it repeats here in a period of 2. See, down, up. So what I want to kind of show you is the tools that we have. So in here, there's a sine animation, a virtual oscilloscope. I haven't done those ones. Take a look at that, but we'll look at these two. There's an animation. Let's do this one. So this is taking the unit circle, and as you notice, this is going to be a cosine animation, so I've got it turned on here. If I move this A, it's going to make the angle, and the cosine is going to get graphed off. So again, just kind of seeing that, remember, graph of a cosine, the x-coordinate is the angle, the y-coordinate is the function. If you want to do the sine animation, you click on here, turn it on, and then you can turn the cosine off, and then same thing will happen as you go through here. It graphs the sine function for you. So it's kind of a simple one, but it's a good one to maybe run a few times because your mind starts to see that the y-coordinates are coming from the unit circle. And on this one, it comes from the y-coordinates of the unit circle, right? Because that's what sine is. When we go to cosine, the y-coordinates are actually coming from the x-coordinates on the unit circle because that's the cosine. Okay. But the one that's really fun is this one, which is transform sine and cosine. And notice it's set up to do either sine or cosine. Cosine's currently turned off. If you click on these, you can turn cosine on. It's a little bit too much to do all at one time. But you've got the standard sine, and then you've got a sine with A, B, and C. Now, this one's a little different. Notice the B has been factored out. So whatever C is, it's directly going to be, let me address that right here. Let me go back. Okay, so there are two versions of this formula. You sometimes will see it written as y equals a cosine b times x minus maybe little c, or they'll still use c oftentimes, but this c is different than the big C up here, right? Because b's actually been factored out. So it's two different versions. It's in a parentheses already. And so in this case, b is, well, it's not the, so that doesn't affect the amplitude or period. Those things are, but in this case, if it's, you see it this way, C is the phase shift. You don't have to divide it by B. Okay? C is the phase shift. Because the B has sort of been factored out to the front, because you would multiply back through by B. And one way to see is if you were to write them in the same, this would be like A or y equals A cosine, distribute the B, you would have bx minus bc. And if you divide this by B, you just get C as your phase shift. Okay, but watch for that. There's two different versions. I just recognize that now, but okay. So then what you can do is you can play with this. So A is our amplitude. Watch what happens if I make A smaller. It compresses it vertically. If I make A bigger, there's my amplitude growing. So you can kind of see, change A and it changes the amplitude back down to 1. B is going to change the period. Watch how that affects the graph. It makes the wave happen sooner if I make it bigger, right? Because that's inside, it's actually dividing by that amount. If I go the other way, it stretches out the period. Okay, put it back at 1. C is a phase shift, and remember the way they have it, it's a direct phase shift. So if I go to the right and make it bigger, it will actually should shift it to the, oh, they've got a negative here. So when C is positive, I'm actually subtracting it, which moves it to the right. And if C is, if I go the other way, then it changes the negative to a positive and moves it to the left. Okay, but you can see how the phase shift works. And then they didn't talk about it earlier, but D moves it up or down. So we're adding something and moving it up or down. But I encourage you to go through and maybe play with this a little bit, especially it's kind of a nice little tool if you're doing the homework and you want to see if it worked, see what the graph looks like. And again, just to if you want to change to cosine, just click on these and then click on these to turn the sine off so that you don't have too much going on at the same time. And the nice part is it shows you the standard sine function or the standard cosine and then the transformed function as you go through. And again, A, if you go back and you make it negative, you see the flip. And you can always compare it to the regular function. So that's a nice little tool that's built into Canvas. Takes you to there. I encourage you to use it as you do the homework. Again, in the homework, you'll be either given functions and ask what is the amplitude, period, phase shift, or you'll be given graphs and asked to come up with the function. It goes both ways. Questions? All right. So this is the start of the graphing. We move on. We'll look at the graphs of the other functions as well, how those look, and again, there are combinations of these. And then we'll also be looking in the future at solving trigonometric functions. We can do it graphically by various other methods, and looking at some identities as we go forward. Nice part, the rest of this class is all trig. So it's really imperative, though, that you have a good understanding of what came before this, from the unit circle, what is a sine, what is a cosine, opposite over adjacent, all those kind of things. If you become proficient at those, fairly proficient, this stuff will become easier. All right. What time is it? 9:41, perfect timing, I think. We still have half an hour, so if you want to start into the homework, you're welcome to do that. But that will complete the lesson for today, and we'll be able to move forward.